Sinusoidal graphs. The London Eye has a huge Ferris wheel 135 meters, 394 feet tall in London, England, which completes one rotation every 30 minutes. When we look at the behavior of this Ferris wheel, it is clear that it completes one cycle or one revolution and then repeats this revolution over and over again. This is an example of a periodic function because the Ferris wheel repeats its revolution or one cycle every 30 minutes, and so we say it has a period of 30 minutes. In this section, we will work to sketch a graph of rider's height above the ground over time and express this height as a function of time. Periodic functions. A periodic function is a function for which a specific horizontal shift p results in the original function, f of x plus p equals f of x, for all values of x. When this occurs, we call the smallest such horizontal shift with p greater than 0 the period of the function. You might immediately guess that there is a connection here to finding points on a circle, since the height above ground would correspond to the y value of a point on the circle. We can determine the y value by using the sine function. To get a better sense of this function's behavior, we can create a table of values we know and use them to sketch a graph of the sine and cosine functions. Listing some of the values for sine and cosine on a unit circle. Here you can see how for each angle we use the y value of the point on the circle to determine the output value of the sine function. Plotting more points gives the full shape of the sine and cosine functions. Notice how the sine values are positive between 0 and pi, which correspond to the values of sine in quadrants 1 and 2 on the unit circle, and the sine values are negative between pi and 2 pi, corresponding to the quadrants 3 and 4. Like the sine function, we can track the value of the cosine function through the 4 quadrants of the unit circle as we place it on a graph. Both of these functions are defined for all real numbers, since we can evaluate the sine and cosine of any angle. By thinking of sine and cosine as coordinates of points on a unit circle, it becomes clear that the range of both functions must be the interval of -1, 1. Domain and range of sine and cosine. The domain of sine and cosine is all real numbers, -infinity to infinity. The range of sine and cosine is the interval -1, 1. Both of these graphs are called sinusoidal graphs. In both graphs, the shape of the graph begins repeating after 2 pi. Indeed, since any coterminal angles will have the same sine and cosine values, we could conclude that sine of theta plus 2 pi equals sine of theta, and cosine of theta plus 2 pi equals cosine of theta. In other words, if you were to shift either graph horizontally by 2 pi, the resulting shape would be identical to the original function. Sinusoidal functions are a specific type of periodic function. Period of sine and cosine. The periods of the sine and cosine functions are both 2 pi. Looking at these functions on a domain centered at the vertical axis helps reveal symmetries. The sine function is symmetric about the origin, the symmetry the cubic function has, making it an odd function. The cosine function is clearly symmetric about the y-axis and the same symmetry as the quadratic function, making it an even function. Negative angle identities. The sine is an odd function, symmetric about the origin, so sine of negative theta equals sine of theta. The cosine is an even function, symmetric about the y-axis, so cosine of negative theta equals cosine of theta. These identities can be used, among other purposes, for helping with simplification and proving identities. You may recall the cofunction identity from last chapter. Sine of theta equals cosine of pi divided by 2 minus theta. Graphically, this tells us that the sine and cosine graphs are horizontal transformations of each other. We can prove this by using the cofunction identity and the negative angle identity for cosine. Sine of theta equals cosine of pi divided by 2 minus theta equals cosine of negative theta plus pi divided by 2 equals cosine of negative 1 multiplied by theta minus pi divided by half equals cosine of theta minus pi divided by half. Now we can clearly see that if we horizontally shift the cosine function to the right by pi divided by 2, we get the sine function. Remember, this shift is not representing the period of the function. It only shows that the cosine and sine function are transformations of each other. Example 1. Simplify sine of negative theta divided by tangent of theta. We start by using the negative angle identity for sine. Negative sine of theta divided by tangent of theta, rewriting the tangent, negative sine of theta divided by sine of theta divided by cosine of theta, inverting and multiplying, negative sine of theta multiplied by cosine of theta divided by sine of theta, simplifying we get negative cosine of theta, transforming sine and cosine. Example 2. A point rotates around a circle of radius 3. Sketch a graph of the y-coordinate of the point. Recall that for a point on a circle of radius r, the y-coordinate of the point is y equals r sine of theta. So in this case, we get the equation y of theta equals 3 sine of theta. The constant 3 causes a vertical stretch of the y values of the function by a factor of 3. Notice that the period of the function does not change. Since the outputs of the graph will now oscillate between negative 3 and 3, we say that the amplitude of the sine wave is 3. Example 3. A circle with radius 3 feet is mounted with its center 4 feet off the ground. The point closest to the ground is labeled P. Sketch a graph with the height above ground of the point P as the circle is rotated. Then find a function that gives the height in terms of the angle of rotation. Sketching the height, we know that it will start 1 foot above the ground, then increase up to 7 feet above the ground, and continue to oscillate 3 feet above ground and below center value of 4 feet. Although we can use a transformation of either the sine or cosine function, we start by looking for characteristics that would make one function easier to use than the other. We decide to use a cosine function because it starts at the highest or lowest value, while a sine function starts at the middle value. A standard cosine starts at the highest value, and this graph starts at the lowest value. So we need to incorporate a vertical reflection. Second, we see that the graph oscillates 3 above and below the center, while a basic cosine has an amplitude of 1. So this graph has been vertically stretched by 3, as in the last example. Finally, to move the center of the circle up to a height of 4, the graph has been vertically shifted up by 4. Putting these transformations together, h of theta equals negative 3 cosine of theta plus 4. Midline. The center value of a sinusoidal function, the value that the function oscillates above and below, is called the midline of the function, corresponding to a vertical shift. The function f of theta equals cosine of theta plus k has midline at y equals k. To answer the Ferris wheel problem at the beginning of the section, we need to be able to express our sine and cosine functions at inputs of time. To do so, we will utilize composition. Since the sine function takes an input of an angle, we will look for a function that takes time as an input and outputs an angle. If we can find a suitable theta of t function, then we can compose this with our f of theta equals cosine of theta function to obtain a sinusoidal function of time. F of t equals cosine of theta of t. Example 4. A point completes 1 revolution every 2 minutes around a circle of radius 5. Find the x-coordinate of the point as a function of time if it starts at 5, 0. Normally, we would express the x-coordinate of a point on a circle centered at the origin using x equals r cosine of theta. Here we write the function x of theta equals 5 cosine of theta. The rotation rate of 1 revolution every 2 minutes is an angular velocity. We can use this rate to find a formula for the angle as a function of time. The point begins at an angle of 0. Since the point rotates 1 revolution equals 2 pi radians every 2 minutes, it rotates pi radians every minute. After t minutes, it will have rotated. Theta of t equals pi t radians. Composing this with the cosine function, we obtain a function of time. X of t equals 5 cosine of theta of t equals 5 cosine of pi t. Notice that this composition has the effect of a horizontal compression changing the period of the function. To see how the period relates to the stretch or compression coefficient b in the equation, f of t equals sine of bt, note that the period will be the time it takes to complete 1 full revolution of a circle. If a point takes p minutes to complete 1 revolution, then the angular velocity is 2 pi radians divided by p minutes. Then theta of t equals 2 pi divided by p t, composing with the sine function, f of t equals sine of theta of t equals sine of 2 pi divided by p t. From this, we can determine the relationship between the coefficient b and the period, b equals 2 pi divided by p. Notice that the stretch or compression coefficient b is a ratio of the normal period of a sinusoidal function to the new period. If we know the stretch or compression coefficient b, we can solve for the new period, p equals 2 pi divided by b. Summarizing our transformations so far, transformations of sine and cosine, given an equation in the form f of t equals a sine of bt plus k, or f of t equals a cosine of bt plus k, a is the vertical stretch and is the amplitude of the function, b is the horizontal stretch or compression and is related to the period p by p equals 2 pi divided by p, and k is a vertical shift and determines the midline of the function.